Okay, let's get started. Good morning. All right. So, I hear you guys like trig, and in the next few days, you're going to have trig coming out of your ears, whether you like them or not. So, like them enough to do well enough. That's my suggestion. Okay, so today we're going to look at, by the way, the exam results have not come back yet. I expect them sometime today, possibly tomorrow. Once I get them, I'll look them over, make sure things are graded correctly, the scores don't look weird, and then I'll ask the TAs to post the scores on WebAssign. So expect to see the scores, I would say, sometime in the middle of this week. All right? You will get the test themselves back maybe a week or week and a half from now, sometime in a future recitation session. Okay? All right. So today we're going to look at 7.2. We're going to look at trig integrals. So first of all, there are a lot of trig integrals that we can calculate already. For example, something like this. This is something that we can do with a u substitution, right? And you can see if we let u be sine of x, then du is cosine x dx. So that's nothing more than u squared du, or 1/3 u cubed plus c, or 1/3 sine of x cubed plus a constant c. And as long as one of these guys has a power of 1, for example, if the power of sine went up to 5, we do exactly the same thing. If the power of sine went up to 17, we deal with this exactly the same way. Now, what happens when cosine, for example, gets a higher power? Then we run into a little bit of a difficulty. So, for example, let's bump sine up to 3, which by itself doesn't really matter that much. But then the problem is with the cosine of 4, power of 4 here. And let's try to do what we've done before and see what happens. Let's start with that, trying letting u be sine of x, like we did before. Then I have du equal to cosine of x dx. And then this integral here, let's try to make things fit. I need a power of cosine with a dx to form du. I have 4 of those. So let me break it into cosine cubed times cosine x dx. All right. Now you see what happens. This is u to the power of 3. That's fine. And here, this is du. It's the middle one here that we get a little bit of an issue here. Now the trouble here is, how do we write cosine to the power of 3 as some function of sine, which is our u, in order to integrate. We probably could do it, but it doesn't look that easy to do. So let's try if we switch the choice of u, switch it to cosine and see what happens. All right, so let me write the integral here again. Just a reference. Last time using u to be sine, we didn't go anywhere significantly. So we're going to try letting u be cosine this time. And if u is cosine, then du is minus sine, right? Then let's rearrange that integral again. Here's my cosine to the power of 4. I need one factor of sine with a dx to form du. I have 3. I'll break it into 2 and 1. So then again, this is u to the 4th, right? This guy here, negative sine of x dx is du. I have sine of x, so I have minus du. Now the middle guy here, same goal as before. Somehow we want to write it as something to do with u. I want my entire integral to be in terms of u. So what do you think? How do we relate sine squared of x to cosine? Is there a way to do that? Yeah. Absolutely. Right, this is a very powerful identity we can use. As long as the power is 2, we can relate them around. Compared to the last one here, we had a power of 3. That couldn't be used directly, at least easily, right? So you see the middle one here, after a little bit of work, turns into 1 minus u squared. So let's see what we end up getting. We get u to the 4th. Middle guy is 1 minus u squared. This one is negative du. Let's put a minus out here and leave the du inside. Okay, so that's perfect now. Everything is in terms of u, and then we integrate. The rest of this is really pretty straightforward. And what's u? U is cosine. Minus minus plus. All right, so we integrated it. Right? That's what we wanted, and there's the answer. Okay, so let's look at what we did. We tried 2 choices of u. That's all we got. And one of them didn't lead us anywhere easily. The other one, by using a simple identity that we all know, it gave us the solution. And what did we do? We look at the situation here. One of these guys has an odd power. If we let u be the one with the odd power, we don't get anywhere. But if we let u be the one with the even power, then we could do something about it. Right? So that's actually something that would work for all the situations like this. Suppose you're integrating sine to the power of m times cosine to the power of n. N and m can be equal, but chances are they will not be equal. If at least one power, m or n, is odd, like what we got in the last example here. Last example, we have sine getting an odd power, cosine getting an even power. We want to let u be the guy with the even power. So what we do here is to save a factor of the one with odd power. Right? So here, see, in the last example, we saved one factor of sine. It started with an odd power. And then we rewrote the rest of this using an identity and letting u be the one with be the other one. Let me write this down. Then we use identity. So we got another example. See if this thing works. Here we have sine with the power of 2 and cosine with the power of 3. Right? The rule says if at least one of these is odd, save one factor of the one with the odd power. So cosine has an odd power. We want to save one factor of that. Let u be the other one. So in this case, sine, right? And then we go ahead and change everything over to u. So we use identity for the leftover cosine squared. This is du already. And now we got sine and sine. The one factor we saved that goes into du. So we leave that alone. But everything else has to be in terms of sine in our example here. So u squared, 1 minus u squared du. Simple integral again. And in the end, we get this thing. Okay? All right, does it make sense how this works? When at least one of them is odd. When they're both odd, it doesn't matter which you choose. You just choose one, save a factor, and do the rest. Both even. We're going to cover that in a little bit. Any question on this, how this works for the at least one odd? Yeah. The odd powers, well, here we have a higher power. You mean compared to the other one or just in general? Just in general? Yeah, it doesn't matter. So I think I have an example there. Let's see. Yep, I do. Let's look at that one. And then we're going to look at what happens when they're both even. Okay? So you see, it doesn't matter what power it is. As long as it is odd, when you take one away, you're going to have some kind of even power left. And you can always use that identity to get rid of it. So cosine has odd power, so we save one factor of that. And let u be sine. du is cosine of x dx. So there's my du. Then for cosine to the fourth, think of it as cosine squared squared. And we know what to do with cosine squared. It's 1 minus sine squared, and then squared again, right? And now we make our change. U squared, 1 minus u squared, then squared, du. And now the answer to your question is right here. As long as this power is odd, it doesn't matter how high it is. We end up getting this kind of expression with some kind of power. The problem is how do we deal with that? But that's a relatively minor issue compared to how we integrate this thing in the first place. So if this were like a 12 or something, we would have probably some issue multiplying it out. But as long as the power is not too high, we can deal with it. Okay? And then the rest of this is pretty simple, straightforward, so we're going to skip that. The idea is on how to get to this point and then integrate. Does that answer the question you had? Yep. So it'll affect the practicality of this step here. Yep. Okay, now let's look at what happens when they're both even. If they're both even, we still need some kind of identity. We can use this one and or this one. Sometimes we could also use this one. This is when they're both even. We have choices of what to do with either of these two. Okay, let's see what happens if we had this kind of situation. Okay, so we're not going to go too crazy yet. Let's just go power of 2 and power of 2. Notice what happens if you use these identities, the top two at least. If you use them directly, then both of these will turn into something to do with cosine of 2x, which is something we can integrate right away. So let's just go ahead and see what happens. Sine square here, let's do that. Cosine. And now I see I have a factor of 4 in the denominator. Let's take that out. And then inside, I have 1 minus cosine 2x times 1 plus cosine 2x. So I do 1 minus cosine 2x squared. And now I have two choices left. I can use the half-angle identity for cosine one more time, or I can go back to sine squared and use the other one. Because I know 1 minus cosine squared is sine squared of the same angle, which is 2x. Okay, so if I do that, then I would use this identity here. This seems simpler, right? I don't have to deal with another 1 in front of it. Yeah? I already took the 2 out. See, 2 and 2 and... Oh, here. Okay, you're right. Absolutely. Yeah, missed that. Thank you. Got it. I missed that. Right? I have two choices. I can do this and I can do that. What? Absolutely. Yep. Okay, so there's no 2, right? No 2. This is just a straight, regular Pythagorean identity. So it's this guy I'm using for that step. Yep, see that? So this gives me that, then it gives me this. Starting to look like a football play here. I'm not going to comment on our football team. All right, so is it clear what we did here? Good? Okay, so let's then go ahead and use this identity one more time. So that's 1 over 4 integrate 1 minus cosine what? 4x, right? I started with a 2. This says that whatever I started with, I double that when I change it. So I had a 2 here, so now I double that. And then here's the 2 again. Okay, then we carry on. Let's take that 1/2 outside. And then we integrate. Notice we're not doing any substitution here, right? We only have cosine of something. It doesn't have any power higher than 1. That by itself is something we can integrate. So there's no substitution involved. So I integrate 1, I get x. What do I get when I integrate cosine of 4x? Positive or negative? I was expecting a more confident answer. Positive or negative? Do I keep my minus sign or do I change it to plus? I keep it. I keep it. That's right. Okay, guys, that's something you need to be comfortable with. I really shouldn't be hearing half and half or 70-30. It should be 100%. All right, so we got to get our trig straight. Remember, when you take the derivative of sine, you get positive cosine. So if I started with a negative cosine when I integrate, then I must have had a negative sine to get me that derivative. But when I integrate sine, then I change the sign. And then the 1/4, where did this 1/4 come from? That's the chain rule, right? When you take the derivative, you need another 4. That cancels the 1/4. So there's my 1. Okay. So what do we have? We have this, right? 32. Gee. 2. Thank you. Okay. Questions? Okay, let's bump one of these guys up to another higher even power. So let's just go up to 4. Let's bump cosine. There are actually a few different ways to go about. Let me show you one way to do it. So one way here is to break apart that cosine to the power of 4 into 2 and 2. And then I could use this third identity here for the second and the third terms. Right? So that's the identity I'm going to use for this one right here. So this, think of it as cosine squared of x, sine squared of x, the whole thing squared. So this guy in the middle gets replaced, turns into that, and then we square that. All right, let's see what we get. So here I get sine of 2x squared over 2 squared over 4. Let's take our 4 outside. Okay, so now we got cosine squared, just x, sine squared with a 2x. Now we got choices again. We have these two we could use, or both. And this is one of the difficulties of some of these ones. It is, at this step here, we have so many different choices. And sometimes you just got to try all of them until you find one that seems reasonable. Yep. So for this one, I tried a few of these, and let me show you the most efficient way to do it. So let me copy what I got here before I do any more. If I use the half identity for sine, then I'll end up with cosine of 4x all over the place. And then I have cosine of x, cosine of 4x all over the place. Not very good. But if I use the half angle identity for cosine, then I'll get cosine of 2x of something all over the place. Here I have sine of 2x, which turns into cosine of 2x by the Pythagorean identity. So that should work out. We'll take a look. And then here we have, I'll pull that 1/2 out again. And then I'm going to distribute the cosine squared into here, and at the same time splitting up the integrals. Splitting into 2 integrals. Kind of like that. All right, so let's look at the second one here. How should I integrate the second one? Yeah, u substitution would do it. Let u be what? Sine, yep. You see, this is the first example we look at the beginning of this class. Right? Sine squared 2x, cosine 2x, sine squared x, cosine x. Exactly the same thing. And remember, I said, as long as one of these guys only has a power of 1, Just the basic U substitution will take care of that. It's when the second one, when they both have powers more than 1, then we have tricks for that. But here we don't need anything special, just the basic substitution. How about the first one? How should we tackle that? Chain rule, maybe. Can you elaborate? Maybe. Any other suggestion how we can tackle this? The Pythagorean, I can do that. Sure, that's one option. But then I'll get 1 minus cosine squared of 2x, and then I have the same kind of issue here. I still have to square something, yeah. Yeah, let's do a half angle. Let's see what we get with our half angle. So sine squared, sine of 2x, what do we get, plus or minus? Minus, yep. Cosine of 4x, right? Well, I don't need dx. I just want to change that part. All right, so let's see what we get. We get 1/8. Here we get 1 over 4 times this thing squared, 1 minus 2 cosine 4x plus cosine square 4x because squared. Oh, what am I doing? Back up. Stop. No. Oh, my. No. Okay. It was getting too hard, wasn't it? Okay. Now we got to fix it. Fix. All right. Okay. Here we go. 1/8 inside 1/2 1 minus cosine 4x. Right. Then the second one is just straight integration. U squared du 1/16 1 minus cosine 4x dx plus 1 over 8. That I can integrate right now. It probably is. It probably is. Okay, guys, I'm sorry. Sorry. Is that good? Right, I bumped this up to 3. Again, you have 3 down here, so that's a 6. I'm afraid to keep going. Okay, let's just finish this up. Eight times 6, 48. And what was u? Sine of 2x. Cube. Okay, we'll just leave it. All right, so my screw up with constants aside, does the process make sense with the juggling with the even powers? Yes? Okay. I apologize for screwing up these constants. I shouldn't have, but it happens, right? Sorry. Okay, so that's how you deal with both even powers. So now we know how to deal with one odd, both odd, and then both even, right? Now let's look at a related kind of thing. It's not bad, really. Trust me. It really isn't bad. Let me show you why this is basically the same thing we just did. Remember, two things to remember here. If you look at the tangent here, for example, I know the derivative of tangent is secant squared. So if I have tangent to the fourth secant squared, then this is actually pretty easy to do. I let u be tangent. There's my du, and then I'm done. So this is simply u to the fourth du, which we can integrate all day. No, we shouldn't. There we go. Right? So that's easy. It gets tricky when, for example, secant has a power of 3. Then we get a little bit of an issue here. So here's how we handle that. Very similar to how we handle cosine and sine. First, we look at the power of secant. If secant has even power greater than 2, then we save one factor of secant squared, because that's going to become du, and then do identities to deal with the rest. Okay, so you save one factor of secant squared, and then you use u equal to tangent, and then identities to do the rest. So here's even power greater than 2. If it's just even and equal to 2, like in this example, nothing special. That's not bad. I've heard worse. All right, so if tangent of x has odd power, then we save one factor of secant x tangent x, because that's going to form part of du. And then we let u equal to secant of x. And then we use identities. So there are only two possible choices here to look at. Let's see a couple examples. You see, it's really like the sine and cosine one. You save whatever you need to save to form du. This is the general theme today here. Think about if you let one of those guys be u, what do you need for du? And you save what you need. So before we go further, here's the other Pythagorean identity that we're going to need. Let's do both to the power of 4. Okay, so according to what we just wrote down here, first we'll look at secant, the power of secant. Secant has an even power greater than 2. So we save one factor of this. And then we let u be tangent, so this turns into du. That, we use the identity. Right? So this turns into u to the 4th, 1 plus u squared du. And then that's trivial from that point on, but I'll still probably screw up, so I'm not going to attempt it. Let's look at one more example, one quick one before we leave. Again, you look at secant to start. Does secant have even power? No. In that case, we're going to save a factor of secant tangent. But we're going to let u be secant of x. So this has to be turned into something to do with secant. Okay, so we look up here. Tangent squared is secant squared minus 1. So this is secant squared of x minus 1 squared. And this is my du. So that's u squared minus 1 whole thing squared du, which we can also integrate pretty easily. Okay, so you see, it's like a sine and cosine case. Think about which one should be u and what do you need to save. And then you use whatever identity you can find